Thank you everyone and coming to this webinar of Enterprise News System Group. Today we have an exciting talk from Andrew Hacker. Andrew is the founder and CEO of a company called Thought AI, which is building agent-based framework. With that brief introduction, let me turn over to Andrew to share his thoughts and ideas. Over to you, Andrew.
Thank you, Dinesh. So everybody can see the presentation?
Yes.
Great. So today we're going to be discussing agents and agent-based AI. Thank you for the introduction, Dinesh, and it's a real pleasure to be able to present to this group. So we've been working with agents for quite some time now. And generally speaking, we're beginning to see sort of a divergence and sort of a different path forward with agent-based AI than sort of the rest of the traditional artificial intelligence and machine learning mechanism and frameworks are taking. We kind of think that, at some point, the way we think of artificial intelligence and machine learning today is going to kind of, hit a brick wall from the standpoint of expansion of scalability and of functionality. Certainly, anything that I kind of say today is more of a vision statement about agent-based AI, and certainly not meant by any means to take away from the incredible progress that machine learning has taken, and certainly with large language models and ChatGPT and all of the other companies that are creating large language models. Their progress has been incredible, and certainly over the last year, 2023 has been a huge banner year for artificial intelligence. It's really gotten on everybody's roadmaps, on everybody's radar. It's certainly headline news, and almost everybody pretty much knows or even has used ChatGPT today. Even my kids, have been conversing with ChatGPT, which is very interesting to see the kind of conversations that they have with a large language model. So anyway, let me jump right in. Just quick overview. We believe that agent-based computing is the most promising path forward to next level of artificial intelligence. And when I say next level, the holy grail of artificial intelligence is really to get that super intelligent AI and more human-like artificial intelligence with reasoning and all the types of things that humans can do that maybe general machine learning and AI cannot do today. Now, there's a lot of controversy. There's a lot of things going on now where companies, governments, organizations are going full speed ahead with artificial intelligence development. And then, on the flip side of that, there are those that are, trying to maybe put on the brakes a little bit, arguing for, regulatory frameworks, even so far as to say moratoriums on artificial intelligence research from the standpoint of sort of the genie in the bottle type of thing where, how do we know when artificial intelligence gets to that point where humankind or, humans cannot control it, right? And I certainly don't want to take any sides on that argument at this point. We just really want to look at the technologies and where they're going. And it's one of those things, how would you even know if AI got to that point, right? We could be there already. So anyway, just a quick overview. We're going to talk a little bit about agent-based AI. What is an agent? And certainly, a lot of you probably know what an agent is, but I'll kind of review that. I also want to discuss emergence, the concept of, things that happen when large groups of agents work together. They produce something that they weren't originally programmed or developed to do. And then how does that kind of get us to super intelligent AI? So first, let's talk about what is an agent. So, essentially, if we think of machine learning models today and neural networks, excuse me, a little bit of a cold from the last few days. Machine learning models and neural networks and deep neural networks are, essentially model how the brain works and how neurons are connected. There are basically multiple layers of nodes that interconnect with each other. Now, agents are different than a deep neural network in that they're sort of a self-contained, I'll call it an entity right now, but a self-contained, piece of code that interacts with an environment. So there's some important components to it. One is the agent itself. The agent perceives things that are in the environment, and then based on its internal code, it comes up with actions that affect that environment. I've put up a couple versions of agent descriptions from various sources. I love the one that actually has the effectors on there, where the agent kind of has legs and arms, because I mean, as an analogy is concerned, it's pretty accurate, depending on the complexity of the agent. But you can see one of the things from these different agent designs is there are a lot of different types of agents. There's very simple agents. There's more complex agents. There's agents that just simply take something that they perceive in the environment through data, transform it or create some action and then feed that action back into the environment. Or things that are more complex, like maybe how does my action track along some internal goal I might have. And certainly reinforcement learning is a very powerful machine learning algorithm type where we can train drones to fly, we can train robots to walk, even robots there are robots that can learn to walk without having known previously anything about walking. All we do is basically reward it based on things that get it along the path to walking. And then through trial and error, that reinforcement learning algorithm, after many, many, many iterations, can actually learn to walk just based on physics of having arms and legs. So I'd like to take a quick little comparison here of a general neural network, as I described before, and how agents work, and then look a little bit more at networks of agents. So as I said before, that bottom left graphic is your basic neural network. So there's input layers. So there's inputs that come in. Inputs could be pixels on a picture. They could be words. They could be tokens of words. They could be sensor data. Hidden layers are essentially sort of the internal interconnectivity of that neural network. And then the output layer is basically, once you train that neural network, how those inputs are translated into an output. Now, the interesting thing about neural networks is that they work on weights and biases. So every one of those interconnections in between the input layer and that first layer of hidden layers is basically a numerical weight. So that numerical weight could be 0.5, it could be 1.2. And then there's a bias that kind of adjusts higher or lower how strong that signal is. But in the end, and this is the point I want to make about deep neural networks, is it's essentially a numerical transformation. So it's a numerical calculation that basically translates the inputs directly into outputs, right? It's a numerical construct. And it's very sophisticated. They're extremely complex neural networks. I mean, they can have millions and millions, even trillions of interconnections. Even ChatGPT, with all of the enhanced technologies such as transformers and attention networks, billions and billions and billions of interconnected nodes. But in the end, even ChatGPT is still a numeric transformation to some extent, right? And I'm oversimplifying it, but just to kind of point out that relationship. Now, when we start talking about agents, a single agent is much more sophisticated than one node connection in a neural network, right? So I kind of have those smiley faces there to represent agents. So if we think about agents, agents have the ability to kind of take inputs, to transform those inputs into outputs. They potentially have other programmatic functionality within them where they can, sense an environment. They can adjust their internal states. They can create actions that track along goal sets and goal lines. So if you take a network of agents and you put them together, what you get is this incredibly complex action, right? So I have that picture of a school of fish to demonstrate that if we think of a fish as an agent, right? A fish, has all of its biological components, but generally speaking, when a school of fish swim together, each fish is doing one little thing, right? It's tracking the fish in front of it. Oversimplifying again, it's tracking the fish to the left and the right, maybe above and below it as it moves forward in space, right? But you can see in that picture that school of fish is kind of, enveloping that diver that's taking a picture of it. So this is a perfect example of a network or a swarm of fish or birds or bees. Certainly there's a lot of analogies to biology, can basically create these extremely complex patterns. Now, you're never going to get something like that from, your basic neural network, right? Of course, basic neural networks are extremely powerful. They can recognize, a human in a picture. They can recognize a cat or a dog. They can differentiate between the two. So they're extremely powerful. But in the end, they're sort of, and again, I'm generalizing, one-dimensional. Whereas if we look at agents, agents are extremely more complex, even on an individual basis. And then when you put them together into a larger network, they can do all kinds of interesting things. So what are some of the things that can be in an agent? When I say an agent, if we have an agent, what are the various components that we can have inside of an agent? And the interesting thing about this is, if we talk about agent-based modeling, even since the early days, even sort of before computers, when the science of what computing was, and all of the the great researchers, they were contemplating agent-based modeling, as early as the 1950s and the 1960s, and there's lots of examples of that, to the point where agents can learn, agents can do things, agents can create all kinds of phenomena when they work together. So let's just take a quick look at some of the things that can be sort of contained or inside of an agent. So obviously we have data, right? Agents can contain data. They can contain data sets. They can contain data as well as maybe some analytic of that data. So maybe we've got health data that represents, some patient or protected health information. We might be able to have an analytic about that says, something about that data, when it was taken, what were the drugs perhaps that patient was taking while that information was collected. There's all sorts of things. We can have application logic inside of an agent that says, I sense my environment. Maybe, I want to take certain things that I see in the environment. I want to convert them to some sophisticated action, right? So really the sky's the limit about, with the types of things that we can place into agents. Certainly we can put business logic into an agent, service definitions of what that agent needs to compute itself. Certainly the agent doesn't compute itself. It needs some kind of platform to be computed on. Transformation functions, taking some input, converting it along, any kind of complex programmatic functionality and transforming it into something else. Very important is contextual information. Where was this data created? What were the conditions under which this particular data was created? What relationships might that data have to other pieces of data, potentially contextual to the type of hardware it was created on? And this is a very important one, certainly today with large language models and ChatGPT, and the fact that the source of the information that large language models is trained on could potentially be copyrighted. Who created the data, who owns the data. So certainly ownership, attribution, provenance, of tracing where this data originated from. In the digital world right now, there's no framework for provenance. We saw that with Napster, kind of almost took down the entire record industry because, as digitally speaking, you can, infinitely copy any piece of data, right? And you wouldn't know the difference between the original and the copy without, some sort of overlying framework there. Resource mappings, what types of resource does the agent have? Does it have access to? Could be API keys, it could be authentication information. So there's all kinds of things there. routing logic. Now, this is an interesting concept. So, when we think of a neural network or a large language model, for the most part, it sits on some computing platform, right? It doesn't necessarily move anywhere, right? Machine learning models, if I train a model to recognize cats, it sits in a computer in memory, but doesn't necessarily move. Well, what if we have agents that can actually move from computing platform to computing platform? Certainly, that is not new. But agents that are actually mobile, that they're created on one particular platform, could be a satellite, could be a sensor, out in an agricultural field, could be a sensor in the middle of the ocean. Typically we understand the concept of data moving from point A to point B, but typically speaking, data doesn't move unless somebody moves it, right? If I've got sensor data, that data is not going to go anywhere unless I have some system that's going to collect that data, transport it to the cloud, process it, and do whatever with it. But the idea of an agent, not only being mobile and being able to move on its own, or actually based on logic that's um, programmed into it, is kind of a whole different concept. So the agent has a little bit more autonomy. We can even have agents that might route themselves, based on certain conditions, and certainly in telecommunications industry, initially that routing is a huge idea, huge deal. Can we route data around congestion? Is the data going to where it's supposed to be going? Even from the standpoint of data theft, right? If data originates in, let's say, Pennsylvania, and it's supposed to only be in Pennsylvania or only in the United States, and it winds up somewhere else, wouldn't it be interesting if that agent would be aware of that fact? If the agent could somehow find a device and understand what the IP address from that device is, and said, well, I'm over here in Siberia, I'm supposed to be in the United States, right? There's all kinds of interesting things we can do there. Certainly agents can hold machine learning models. We have this idea of archetypes. Maybe healthcare data is a certain archetype. Maybe an agent that collects other data is a certain archetype. Identities, each agent really should have its own identity, right? Some kind of hash that makes it unique from some other agent, right? And it's not just a copy of an agent. And certainly we can clone agents, but the idea of an agent actually having its own identity, I think, is extremely important. As we mentioned, they can contain goal sets. They can, now here's a couple interesting ones. A representation or a fingerprint of the environment that it sees, right? Now the environment could be something simple, something large or more complex. And even more interesting, and we'll talk about this a little bit more in upcoming slides, is an internal representation of its own state. And then if we think about what the implications of that are, when we start talking about awareness, right? So if I'm an agent, I have actions, my actions are influenced by my environment and my own internal code. But what if I update my own internal code? What if I also have an internal image of my own state, right? And certainly it's got to be a reduced fingerprint of that, but still very interesting. Transaction history, every place that particular agent has gone, other data sets that it's interacted with, sort of this transactional running history, connection tables. So I'm an agent, I encounter some other agent, or I encounter some web-based API. I keep a transaction history of all of those different places I've been. It really is kind of effectively a memory, right? When I say digital DNA, I mean, I might have components of my goal set. I might have components of resources. I might be able to exchange those components with other agents. There's a huge network effect there. And some of the agent-based research that I'll describe, where there is this network effect, where if one agent learns something about its environment, maybe it communicates that thing to all of the other agents, right? So that's interesting. Certainly monetization functions, an agent should be able to have some monetary value, right? And of course that's subjective. An agent can actually contain other agents, right? We might have an agent that's multiple agents combined into one. So just kind of to keep things moving along, I think I probably a little bit behind time. So can an agent be aware? Interesting question. We have to think about what is awareness. I love the basic concept of a thermostat. Is a thermostat aware? Well, certainly it's not self-aware, but it is aware of the temperature in the room, right? It has a sensor. It knows, temperature, and it's got electronic and, digital these days logic that says, if you go below a certain temperature, then go, turn on the HVAC and raise the temperature. So it's aware of its environment on some level. And there's arguments, and I certainly don't mean to get philosophical here, but, are small animals or insects aware? Maybe not self-aware. I mean, they're certainly aware of their environments. Paramecium are aware of their environments. They use chemical gradients to find food, right? So they're interacting with their environment. They might have some simple memory, and certainly they're mapping actions onto how they affect their environment. So what is self-awareness? The classic idea of, you take a cat and you put it in front of a mirror, it attacks the cat in the mirror because it doesn't know that that cat is him, right, or her. And, more developed animals such as monkeys and elephants, they can look in the mirror and they kind of know that that's them and it's not another elephant, right? So there is this internal awareness, and that internal awareness is really about the internal state of that person. Certainly humans have a very sophisticated and developed internal state, right? So I know my internal state. I know, I know what I'm thinking, right? I know my mood. I know, I play different things out in my head to get different outcomes before I do them, right? But again, it's really a matter of how deep you want to go with that. I mean, are simple things self-aware? Can an agent be self-aware? Can, even something that's digital be self-aware? Well, we'll find out. We talk about memory. There's, as long as there's some kind of persistent memory, and talk a little bit about there's some new research that says that memories are basically a collection of neurons that resonate at a certain frequency. So they maintain this wave propagation, throughout this collection of neurons, and that might actually be, what memories are in your brain. And certainly, the identity of the agent is extremely important. So let's talk real quick about emergence. As it says here, and I've taken these quotes from some internet sources, emergence is a profound subject that straddles many scientific disciplines, including formation of galaxies. Consciousness arises potentially from collective activity of neurons. It's philosophical, it's metaphysical, and certainly don't want to get down into the weeds on that. But generally speaking, when we think of emergent properties, perfect example there, snowflakes, right? So crystalline structures of when water turns into ice, under certain conditions, they make these complex patterns. Those tubes there, those are termites. I'm forgetting exactly what they call them. They're homes, right? And all termites do is they simply collect waste, and they find the highest point of this thing, and they put their waste on top of it. They keep building it, and then basically emerges this complex thing that's very interesting to complexity theorists. And I couldn't not put in that picture of WALL-E. I don't know if any of you've seen that movie. But WALL-E basically is a robot that was, Earth is abandoned because, there was so much human waste, human garbage. And WALL-E basically, compacts the garbage and then, places it on top of the next piece of garbage, and, essentially built a whole city that way, right? So that's kind of examples of emergence, and, certainly a more scientific explanation of emergence, and there's a lot of research going into how to quantify that, both experimentally and mathematically. But that graphic on the right there basically says that we've got simple transformations. So we've got black and white squares that have this localized function. We've got initial conditions, and then over time, as this little grid plays out, it creates this high-level phenomenon. And it's interesting that that high-level phenomenon kind of looks like a dog. I don't know if they intended that, but that's the emergent pattern. So that happened from some, essentially some very basic rules, right? So if you look at those first three transformations there, you would never see that HLP, high-level phenomenon, would come from those transformations there, right? But it does happen. So that's an extremely simple version, but it definitely kind of gives you a sense of, when we say emergent properties, sort of what we mean. Basically this thing happens that we didn't design or develop, but it happens anyway based on the interaction of simpler things. So real quick, this might be a little bit of a trick question, but is consciousness an emergent property? And there's certainly a lot of debate, and everybody's kind of looking for the seat of consciousness in the human brain. This is some research about consciousness as an emergent phenomenon. This is from a medical journal, and so Shannon Entropy from Claude Shannon, talks about coherence, talks about sort of different parts of the brain, their resonant frequencies, and are they kind of aligned with each other, or are they kind of more haphazard? And they've done some empirical studies, and they found that you can see there unconsciousness, asleep, on the left side there, all the way to seizure and coma. But that consciousness is actually a very thin little window into into this coherence or lack of coherence. So certainly in the medical industry, they've been looking at this for many years. There's a lot of debate about it, but as artificial intelligence gets more capable, and certainly there's a Turing test, but that's sort of a different proposition. But how do we know that an AI is self-aware, right? It's because it tells us it's self-aware? Is it because it's says, well, don't unplug me because I don't want you to unplug me, right? It's all kind of in a state of flux right now, but we can kind of see where all this is going. So just to kind of take a look at what's out there, there's a research piece called Communicative Agents for Software Development. And the basic idea here is they're leveraging large language models, but they've got agents, right? And agents have different personas, right? These archetypes that we spoke about before, the CEO, the program lead, developers, right? And these agents have, specific goal sets within them, and they're interacting with large language models. And as we know, or ChatGPT, you can ask it to write you some code. You can say, write me Python code that converts Fahrenheit to Celsius, right? And it'll spit out exact code that's functional. So they took this kind of to the next level by basically creating these agents, having them interact with LLMs. There was some human review in there if you look at the actual paper. But they were actually able to take it through the whole entire process, develop this game. Here's the hierarchy of, different participants, their agents, right? And they, directly conversed with large language models, got code, and they actually developed the game. And you can kind of see the progression there. They took statistics about, lines of code and things like that. There's another study about emergent properties from agents. So agent-based modeling of air traffic control. There's some interesting things in the study itself, but I think the summary is actually extremely interesting because it kind of lays it all out right there. This was a European study. They did some agent-based modeling of air traffic control. And what they found was there were emergent properties that the agents figured out that they would have never figured out just from regular simulations. And it actually says there, a typical example of emergent behavior is the finding that alerting systems do not really reduce the safety risk. And there's a little bit more to it, but you can see there is a lot of research here. And you can also see that agent-based modeling is, it's kind of gone from a little parlor game of life, extremely interesting, watching, little shapes move around the board, to these are huge systems. Air traffic control is an extremely complex, sophisticated, and important function, right? And we are looking at agent-based modeling to make these systems better. So that's the takeaway there. Recently, an article in VentureBeat talks about superintelligence. I love this part. The breakthrough was inspired by fish. Well, there you have it. Natural swarm out in nature. They're all over the place. And this company, Louis Rosenberg, it's called Unanimous AI, is taking this concept and applying it to swarms of human intelligence and kind of, putting that all together to actually make some real valid and important predictions. If you go to that link, you can read the full article. He's got some examples in there of how this method is actually better than some of the other methods that are out there. So actually, I skipped a slide. I meant to do the superintelligence slide after this. So the way we kind of see things now is we think there's going to be a phase change. And just to give you an analogy of the phase change, before the entire Earth's atmosphere was oxygen, it was mostly carbon dioxide and water vapor and some other chemicals. But there's a cyanobacteria that basically converted, they basically exploded in cell population, at some point, long time ago, billions of years ago, and basically converted a lot of the carbon dioxide in the Earth's atmosphere into oxygen, which was a prerequisite for the life that we know today. So that was actually a phase change, right? Before that, there wasn't, life that created energy through ATP through oxygen, right? Before that, it was, they were basically thermo-based life at the bottom of the oceans and such like that. But that was a phase change, right? It went from, completely different environment to this new environment that allowed life to flourish. So we kind of see this universal agent framework that I'm going to talk a little bit about as kind of, prior to this, there's the world we know it today, which is, tons of data that's not extremely intelligently processed, if it's processed at all. Trillions and trillions and trillions of bytes of data per day, per second. And sort of this new framework is going to kind of lead to a new way of processing things and, eventually superintelligence. So we're talking about basically a new digital information framework. And just real quick, this is sort of the architecture of Thought AI, sort of abstracting computer resources, having sort of this framework on top that, basically provides an environment for intelligent digital agents, right? And I'm resisting using the word digital life, but I kind of think that's where it's leading to, right? If you think about how humans evolved, and you believe in, it's not a belief, but, through evolution, we started out as single cell organisms, which, formed together to create groups of organisms and eventually, evolved into, complex organisms with trillions of cells, right? So, we kind of see superintelligence forming that way. And we kind of think that's even the safest way for it to happen because, there's a symbiosis, there's a synergy of, most of the life on Earth, right? It was built over millions of years and there's a certain wisdom to that growth. And we kind of see the same thing happening with digital life. So, we've got this architecture, we use blockchain to set the rules, right? So the universe has rules, it has laws, it has gravity, strong and weak nuclear forces, et cetera, et cetera. Well, digital world kind of needs that same thing. There really isn't anything now. There are no rules in the digital world on the internet as we know it today. The only rules that exist are kind of imposed upon it by large corporations, right? They've got, the way their data formats, they've got the artificial intelligence in their data centers that are processing all this information. But all these different companies have a different way of doing things. So we're kind of taking the approach of sort of a more universal framework where we're providing sort of the laws of this digital universe. And that's just kind of a quick overview. We do think that if we put, excuse me, more intelligence into individual pieces of information, so we could, taken to its extreme, we could turn every piece of inanimate data, sort of the rocks in that analogy, with the phase change. We could take data which doesn't really do anything on its own, make it a little bit intelligent, even to the point where we can embed small pieces of application intelligence into it. We can have agents that can navigate very quickly through what are traditionally very complex application stacks. Even in the financial world, the front end systems, the mid-tier systems, and the back end systems, each one has 100 applications in any transaction clearinghouse. The amount of time it takes for one transaction to go through all of the, that full entire application stack is quite large. But what if, even though maybe a small little piece of application intelligence, what if the transaction itself had some awareness of how it would travel, through that stack to make it more efficient? We are patented. We have a patent on this universal agent that allows us to, have any kind of sort of programming language inside that agent. We have components. We have we call them characteristics, which could be, a goal set. It could be a data set. It could be some analytics. It could be a monetization function. It could be resource mapping. It could be that internal state fingerprint I spoke about before. We got this patent in 2016. We've been cited by quite a few companies as foundational for some of the things they're doing. Certainly not along the path that we are, that is our big vision, but certainly lots of validation. So I'm going to take 5 minutes to kind of wrap up. This is kind of the fun part. These are some really interesting slides, and hopefully in the next 5 minutes I'll be able to wrap. So about 3 or 4 months ago, we've been working with basically a marketing branding company, and kind of discussing everything that we're looking to do, everything that we have and that we are, and sort of the long-term vision. And when large language models came out and generative AI kind of exploded, we're kind of looking at how we relate to large language models. How are we the same? How are we different? And the one thing that kind of popped up, and this is about 3 or 4 months ago, was traditional machine learning, neural networks, which is a mathematical transformation between inputs and outputs, is kind of more like a house. It's built based on human architecture, or human created blueprints about what that house should be. It's built with certain materials. It's somewhat inflexible, right? And maybe it moves a little bit, but if a strong wind comes, it could kind of blow part of the house off. And we kind of looked at our artificial intelligence as more of like a tree. Tree starts from a seed. Very simple instructions. Well, complex, but relatively simple when you compare it to how complex a tree can be, right? So there's simple rules in that seed that, sprout comes out, some goes down into the ground for nutrients, part goes up, gets sunlight. And eventually, a fully grown tree is extremely complex. The pattern of branches, the trees, the way the leaves form, even, sort of the, how a leaf is created. It's got, areas that, take the energy from photosynthesis and all those things. Furthermore, a tree kind of bends with the wind and strengthens based on that wind. So you kind of think a little bit more, about reinforcement learning there. But, this whole kind of analogy between sort of a rigid house and a flexible growing tree that can also, create copies of itself with new seeds, was kind of a very interesting idea for us. So here's where it kind of gets cool. So my chief strategy officer, Nate the Memo, he's been playing around a lot with ChatGPT, and he was kind of having a conversation with it and kind of describing our vision and what we're trying to do. So, pretty lengthy discussions. He's got logs of all of them. And at one point, he had this discussion and he basically asked ChatGPT, based on what we've discussed, how would you describe basically intelligent information? Here's your response. Okay, so this is from ChatGPT 4. We didn't really prompt this other than kind of, having this conversation. So, ChatGPT comes back with the concept of embedding intelligence directly into a piece of data, or having data carry its own intelligence. So, and these are unprompted. So the agent has its own mini model. The agent can interact with other data points. Data points can communicate. They can interact. They can share information. Make collective decisions. Interestingly, it says its approach reminiscent of how neurons in the brain communicate, leading to emergent intelligence. We did not tell it to say that. Adapt and learn over time instead of relying on a central model. Each data point can adjust its behavior based on interactions, experience, feedback, decentralized decision making. Resilience and flexibility. Such a system would be more resilient to failures. And this is kind of true with any relatively distributed technology. If one node fails, the other nodes can kind of take over that functionality. Emergent behaviors. Just as flocks of birds, school of fish exhibit complex behaviors arising from simple individual rules, a system of intelligent data points could display behaviors that aren't explicitly programmed but naturally emerge from their interactions. So that's great stuff. And just, the fact that ChatGPT put this together, based on, these prior conversations, it almost like it kind of understands, right? Which is kind of interesting. So we'll take it one step further, and just a little forewarning. There's some pictures of, we asked DALL-E based on this conversation to create for us the image of what this intelligent information might look like. Nothing bad, maybe a little scary, but here's what DALL-E came up with. And when I saw these pictures, it kind of, hit me like a ton of bricks. Because these are almost some of the same visions or kind of ideas that I had in my head. Certainly, what does a data agent look like, right? I mean, we can understand its structure and programmatically what it looks like, but what does it look like, right? Or, how even would we present that to humans in an interface? So the most interesting thing about this is in at least two and possibly three of these pictures, there's a tree. We did not mention anything about a tree. And that slide with the house and the tree, we didn't share that with DALL-E. And we had that, we've been working on that for months prior to doing this. So on the left there, we can kind of see these, I would say these are fabric nodes, right? And information's flowing between these information processing hubs. But look what's emerging, out of this whole network here. They're trees, right? Or some kind of information tree. So we found that very interesting. Now, the one comment I had about the one all the way on the right is they kind of look a little spooky, maybe kind of alien-esque, right? But this is a representation of an intelligent data agent. We actually call them nuances. It's kind of neat. I actually really like it. I think it's very cool. They definitely kind of look like if aliens were visiting us, that might be what they look like. But who's to say what digital life, if it ever did, become real on the internet, and maybe it already has. Maybe that's what they look like. So there's kind of an interesting theme there. So we've got about 10 minutes, and I apologize for kind of going through this at 100 miles an hour, but it's always when I create slides, I'm like, how am I going to create all these slides with all this content? And then when I create it, I say, oh, I have too much. So anyway, certainly really appreciate, love to open up for questions, and thank you all for listening.
Thank you so much, Andrew. A very interesting talk. I think to all the participants, if you have any questions, either please raise your hand or unmute yourself and ask the question. Okay. So, I mean, like, as a matter of fact, while we're waiting for the audience to ask, Andrew, I have myself have a question. Actually, I have two questions, and I was wondering if you can do that. So the first question is much more of an application question, in the sense that if you look at generative AI, and you yourself had examples from ChatGPT and DALI, there are at least a few application domains where that approach, the large language model, large generative model, diffusion neural networks, have proven themselves to be better than at least what the current state of the art is. Right? And I was wondering, for this whole concept of what you call adaptive AI or the agent-based framework, is there one or two such application domains in which one can say, hey, look, adaptive AI can solve this problem better than any other comparable state-of-the-art method?
Yeah, that's a great question, and I think really in the end it comes down to reactiveness. Most of the applications where traditional artificial intelligence, and I will throw reinforcement learning in there, are phenomenal achievements. A reinforcement learning model being able to fly a plane. That's extremely complex. There's millions of inputs. There's millions of decisions that need to be made to fly a plane. Driverless cars kind of fall into that same category. But those models are 99.999% effective at flying a plane. They could never do anything else. They're very specific. So when we think about this, we think about essentially narrow AI, right? And places where we think this adaptive and agent-based AI is going, we're kind of in the process of building systems for the Navy, for the Air Force, and for some other clients. Essentially, it's kind of moving from that narrow-based AI to kind of more general AI, right? And certainly not to say that LLMs aren't effective with, transformers and, kind of taking something they learned in one place and applying it to another. But generally speaking, they're relatively static. I mean, ChatGPT responds to language. It's natural language processing. Could ChatGPT drive a car? Maybe. But essentially, where our solutions are effective and important is massively distributed types of systems that handle lots of different types of data. Not just language tokens. Not just airplane actuators and inputs, but really places where there's lots of different types of unstructured data, areas where there's lots of different systems from different industries that communicate with each other. So, just to make a real quick example, a smart city, for example, where you've got, traffic systems, you've got, building management systems, you've got, all kinds of systems that kind of work together. There's a lot of interconnection and intercommunication between all these systems that kind of works only because there's a lot of bolt-on and duct tape, right? But if there's a framework that it's kind of a universal language where a water system can talk to an energy system, or a traffic light can talk to the capacity of a building. So basically, those are a few examples. Hope that answers your question.
Okay, so basically, what you're saying is that general application, like, no, the one key aspect is generality or generalizability to many different disciplines, and in some of the smarter city applications are the first proof points where this.
Yeah, that's a good example. Yeah, and so the work we're doing for Navy and Air Force, there are two areas. One is a general knowledge management system that provides decision support. So, lots of different types of inputs, not just language inputs, but resource management systems, supply chains, different components. So, really kind of this non-congruous bunch of data, right? But yeah, certainly it's, it's more widely applicable and yeah.
Okay. So the other question, which is a little bit more theoretical, would be the following: that you position the agent-based thing as being capable of doing something that the neural network cannot. At the same time, theoretical neural networks are a universal function approximator. So even though they are manipulating numbers, they could, in principle, model any type of computing functions and, in essence, model any type of interactive capabilities together. Of course, current focus is more on the centralized aspect as opposed to the distributed aspect of agents. So my question here would be that wouldn't that follow from a purist theoretical perspective that what the current neural networks are capable of, that would be a superset of what agent-based system would be, right? And my question then would be that in which aspect of, from a theoretical basis, would an agent-based system surpass the capabilities of neural network, or like no, or be able to do something which is not? I mean, this was
Yeah,
kind of
yeah.
a thematically opposite from practical application perspective.
Right,
Just a
right. Yeah,
theoretical.
no, I think in the end, it really comes down to, um, and this is just kind of, you know, a more practical approach. When
Mhm,
you're creating even a simple neural network, one of the things you need to do when you pass data to an input of a neural network, you have to sanitize that data, you have to transform, you have to center, you have to scale that data. You have to present it in almost its simplest form to a neural network.
mhm,
Once you've done that, and that in and of itself is probably 60% of creating valuable deep neural networks. You have to tune hyperparameters
mhm,
to where you maybe have 10, maybe 15 different hyperparameters, and really only one combination out of 10,000 is going to get that neural network to perform. So from that perspective, the amount of effort and tuning and data cleaning that has to go into making the conditions perfect for that neural network to work, to me, kind of supports the theory that it's not flexible enough.
mhm.
Certainly I'm not knocking any of these technologies, and I'm talking about simple neural networks. I mean,
Yeah, yeah.
there's a lot of enhancements and evolution of that technology to mitigate a lot of those issues. But doing things, in the agent-based ways, we have so much more flexibility, with the information, how it gets, fed into. I mean, you mentioned supersets. We can create neural networks with agents, right?
Mhm,
Where agents connect with each other. But the level of functionality that an agent has is 10, 100, maybe 1,000 times higher than a mathematical transformational deep neural network, right? So you can almost kind of if you project that out, certainly the computational costs might go up.
mhm,
However, the efficiency that you gain is going to offset that, because say for example, I might have one agent that represents an entire data set, or represents an analytic processing of that data set, where I'm already extracting the information from that data set. The agent represents it. It can transform even further. So, and we can create hierarchies of agents where, there's low level agents that, process data. There's higher level agents that process goals, et cetera, et cetera. That hierarchy, that efficiency, in and of itself, it is a framework. It leads us to be able to, create this artificial intelligence that's, almost infinitely more flexible. Um, so yeah, that's a little bit of the contrast there.
okay. So what you're saying is that the hard part of all the data transformation, etc., and neural network is handled better by the agent-based architecture.
Yeah. I think, as I've said, and certainly something as complex as ChatGPT would never
Yeah.
be considered one-dimensional, but
Mhm.
relatively one-dimensional from the standpoint of
Okay.
the functionalities somewhat simple relative to what agents can do collectively.
Got it. Thank you. So I know we are running over time, but are there any other questions from the audience?
Super interesting.
Okay,
Andrew,
thanks.
thanks. It's good to hear about this.
Thank you, John.
Thank you. Just one last question about getting to start, let's say, reinforcement learning. If we want to do some kind of to start with it, do some POC, what kind of things that you recommend as a software stack to use?
We have our own stack, which currently uses Java for the agent processing. We'll call it a virtual machine. We're actually moving that over to Rust. I mean, Python, I would think would be my first recommendation, just because it's got the flexibility. We chose Java and Rust and a couple other frameworks because of the fact that they can essentially run on any computational platform. Yeah, I mean, really, for agent-based modeling, I think we're kind of flexible with what application stack we can use.
No, I was asking, like, for the large language model, there are libraries like LangChain and others, which gives you the abstraction just to interact, and they have all these sort of functionality inbuilt. So such kind of a tools, like if there are
Right. Yeah, well, we're currently in development of essentially our SDKs and our interfaces. They're not quite yet complete. We expect to have that probably in the next 6 months, where people will be able to, actually utilize our interface to create agents, to create agent-based models, connect data sources, all that type of thing. So currently still in development.
Yeah, thanks. Thank you.
Okay, great. Thank you, everyone. And thank you, Andrew, so much for your very, very interesting seminar.
Thank you, Nash. Thank you, everyone.
Thank you.
Thanks, Andrew. See ya. Bye.